Of the formula for the rotational inertia for a rectangular bar. We've got a uniform density bar, density rho, length L, height h, and width w, and we put the axis of rotation at one end of the bar. The axis is vertical, the bar is horizontal. So my drawing's not the best, but hopefully adequate. So our rotational axis over on this end, the bar is extending off to the right. And each piece of mass has a rotational inertia that's found by the value of that mass and the distance squared away from the axis of rotation. So our situation here is we've got various masses, little infinitesimal masses dm, each of those with an r squared. They have to be added up using the antiderivative. So length L is a distance away from the rotational axis, width and height, and we're going to make a change of integration variable here from the dm to dx, and x is going to be a distance along here. Instead of using r, we're out in a straight line here, we'll use x. We don't have much of a circle symmetry, so let's switch to x instead of r's. Let's see how we proceed. Well, we start by realizing the density as mass over volume. If I want a dm, I need a dv, d volume, and multiply both sides by d volume. We get density times an infinitesimal volume would be an infinitesimal mass. Let's see how we can develop that. Well, if we use this little infinitesimal volume here that's shaded in, it's a distance x away from the axis. We'll get to that in a minute. But it has a thickness of dx, and it has a width w and a height h. So that volume, infinitesimal volume, be wh and dx. We do not use L. We don't use the volume of the whole bar. We'll get to that later. But we just have dx here, this shaded infinitesimal volume. So the dm would be the density times this infinitesimal volume, wh dx. Let's put that into the antiderivative and see what happens. We're going to take the antiderivative from 0 to L. 0 is at the far left, and we have length L. That will move this dm from left to right through the bar, doing all the mass in the bar. Instead of r squared, I use x squared. That's the distance. X is the distance away from the axis, so it's just a one-to-one substitution there. Instead of using r, we use x. Then the dm is replaced with density wh dx. We've got some constants. The rho, the w, and the h can be pulled out through the antiderivative process. We have to do the antiderivative of x squared dx. That's simple. So we have, if you do a little review, x cubed over 3. When we do the antiderivative, the power goes up by 1, and then we divide by the new power. In most cases, there's a special case we're not going to talk about here. So x squared becomes x cubed over 3. We have to evaluate that at the upper and lower limits, at L and at 0. Well, if we do that, you can obviously see we're going to get nothing when we do the 0. But put in the L in place of x, and our rotational inertia formula, density, width, height, L cubed over 3. That's not completely useful. It's okay, but it would be better to have mass and length as the only parameters. So we can go back to our density here. The density is the mass of the rod divided by the volume of the rod, LWH. So if I can put that in, I can replace right here for the density, I'm going to put in mass divided by LWH. And now you can see we get some cancellations. The W's cancel, the H cancels, and one factor of the L cancels, and we come up with 1/3 ml squared. 1/3 ml squared is our rotational inertia for a rod with the axis of rotation at one end of the rod. So you could for your own enjoyment, you might put in a more of a cylindrical rod. You'll have to use a volume that's a short cylinder, but see what you get if you do that, and ask your instructor if you have questions.